Hello, my AP students. This is our introductory lesson on Chapter 8, Bonding. We are going to combine Chapter 8 and steal a little bit from Chapter 9 in this adventure in bonding. If you look around you, there is such variety in our world. Metals, the different things at room temperature and pressure that are gases, things that are malleable, that conduct, that are flexible, that are soft, things that have very high melting points, things that have low melting points. All of these properties are partially determined by bonding. This chapter, we will first just remind ourselves of the types of bonds and the definition of bonding. We'll look specifically at ionic bonding, really understanding lattice energies. In covalent bonds, we will master Lewis dot structures and see structures much beyond what you saw in honors. Many situations where we're violating the octet, forming multiple bonds. From the Lewis dot structure, we will apply VSEPR theory to predict molecular geometries and polarity of molecules. We will look at intermolecular forces that stem from that, as well as be introduced to hybridization. We'll look at pi and sigma bonds and just really be able to go deeper into bonding than you ever have before. So let's get some basics. Why do elements bond? Elements bond because overall it lowers the potential energy of the system. Usually we are striving to achieve the octet. Elements have been made that the octet, and when they have 8 valence electrons, that delivers extraordinary stability. They are striving for noble gas configuration. I really like how Zumdahl defines a chemical bond. He says that a chemical bond is the force, or more accurately, the energy that holds two atoms together in a compound. A lot of textbooks define chemical bonds as the link or the glue, if you will, that makes two atoms function as a single unit, or multiple atoms if we have multiple bonding. But I really like that it's this energy that's holding them together. Overall, lowering the energy than if we have two separate atoms together. When they're bonded, they have a lower energy. A lot of other textbooks define chemical bonds as the mutual attraction of nuclei for valence electrons, specifying the pull for valence electrons of a neighboring element. If we have two atoms that do not have their octet satisfied, we know that their nuclei is attracting their own electrons, but within reach, they can begin to attract the valence electrons of a neighboring atom. It's such a coordination between attraction versus repulsion. Now, nuclei attract electrons, but as these get closer and closer and closer, the nuclei will begin repelling each other, and excess electrons will begin repelling each other. If you look further into your packet, on the 3rd page, there's this diagram from your textbook. And so if we look at these being two hydrogen atoms, right now they're so far apart that they're really not influencing each other. But as they get closer, the nuclei begin to pull for each other's electrons. They get closer and closer and closer. The distance at which the potential energy is minimized for this situation. As they get closer and closer and closer, and the nuclei pull on electrons, the potential energy lowers, 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 lowers. Now, if we get them too close, the nuclei are going to repel as well as electrons. That's going to give us a higher energy system right back. It's that perfect distance. That perfect distance at which potential energy is at a minimum is called the bond length. We'll refer to that a lot this chapter. That minimum energy, that energy must be released when bonding is created and must be added to break the bond. That's called bond energy. We'll refer to that more in just a moment. I have some bond energies listed here for some hydrogen non-metal different chemical bonds. I also have on the next page a lot of other bond energies. So we'll take a look at these more in a moment. There are 3 different types of bonds, and the types of bonds can first be distinguished by the elements that make them up. In an ionic bond, it is a combination of metallic elements and non-metallic. For example, sodium chloride. That's the classic example of ionic bonding. We can also have rust, iron 3 oxide. We could have, now that we're getting to Thanksgiving and Christmas, sodium bicarbonate, baking soda, any combination, and there's thousands upon thousands of metal with nonmetal. As long as there is one metal and one nonmetal within our formula, it is being held by ionic bonds. Covalent bonds are nonmetallic and nonmetallic elements. Classic example, water, carbon dioxide, sucrose. Metallic bonding is when we have a metal bonded to other metals or one metal bonded to itself. For example, the copper within a copper wire, iron within an iron nail. It's hard because a lot of times whenever you are mixing metals, you get a mixture, not actually a bonded unit. So metallic bonding is often achieved whenever you have samples of one element with itself, one metallic element with itself. The types of chemical bonds are also distinguished by what is going on with the electrons. When a metal and a nonmetal come together, now we know characteristically that metals have relatively small numbers of valence electrons, and nonmetals usually have larger numbers of valence electrons based upon design. So let's just say, in the case of sodium and chlorine, sodium has 1 valence, chlorine has 7. We know that the metal wants to give away the nonmetal, give away the electron, and how perfect that the nonmetal needs to gain 1. He's fine losing it. He is totally fine because then he has his underlying valence, underlying octet. The nonmetal gladly takes because then it has achieved its octet in this situation. We form a positive and a negative. We know that is the strongest force besides the nuclear force. It is electrostatic attraction that is responsible for pulling metals and nonmetals together instantly. When you have a positive and a negative charge, they naturally come together. Opposite charges attracting, called electrostatic attraction, is what is responsible for ionic bonding. We can actually look at an equation that backs this up. Coulomb's law looks at, now it says energy, but it really is translated and understood to be the force of attraction. We have this constant. Q1 and Q2 are the charges of our ions. So in the case of sodium chloride, Q1, positive 1, Q2 would be negative 1. In the case of sodium oxide, Q1 is positive 1, Q2 is negative 2. R is the distance between the ion centers. In sodium chloride, the distance between the nuclei of the sodium and the nuclei of the chloride. You will be told this. You will be told this, and you want it to be in nanometers to cancel with this constant. Now, if we have a positive and a negative, then energy, your answer will be negative. That reveals the energy that is released, the lowering of energy, or again, kind of the force of attraction between opposite charges. If we have like charges, 2 positives or 2 negatives, it's the energy that must be inputted to get them to come together, which they naturally will not do, of course, where if these are opposite charges, they naturally do pull together. So this shows repulsion as well as attraction due to different charges, backing up the idea of ionic bonding. In covalent bonding, you have nonmetal with nonmetal. Nonmetals need to gain to satisfy the octet. So what if we have 2 things that come together and they both need to gain? How can they both gain one nonmetal will share with the other. A sharing of electrons is what holds covalent bonds and what is responsible for covalent bonding. And it's a sharing of electrons between the nuclei of your ions, between. That is what is responsible for covalent bonding, what is going on with the electrons. In metallic bonding, what if you have a bunch of copper atoms? And we know that metals will only and can only give away their electrons. So, copper, in most cases, gives away 2 electrons per atom. So he's losing 2 electrons, he's going to form a positive 2. Losing 2 electrons, form a positive 2. They don't want the electrons back, but they need them for electrical neutrality. So what happens if we have a copper wire, we have several copper cations that have lost their electrons. They need them there, but no one wants to claim ownership. So the electrons are free to migrate, free to swim amongst all of the cations. We say that metallic bonding is a sea of electrons, or that the electrons are delocalized. They do not have a home. Here, the metal gives to the nonmetal. The nonmetal keeps, the metal has lost. Here, they're shared between their nuclei. They have a place to be. They don't here. And that gives so many of the different consequences to metallic properties. We'll pause here and then go deeper into polar and non-polar covalent bonds, because very rarely do we have equal kind sharing.